Hello everybody, today I'm going to have a project presentation on my project title with on-roll multi-object detection. It's for the ECE588 robotic vision. So for this project presentation, it's going to talk about the introduction of the object detection, multi-object detection, and the training of my tiny-YOLO model, and the system I used like hardware and software parts, and the results and demonstrates videoed. And we have some discussion and of the error and the future work of this project and some reference in the last line. So what's multi-object detection and what's the past work? Actually, for the past popular object detection method for the feature extraction, we like to use the shift descriptor and hub features. And the pipeline for this detection and classification is like the best of breed algorithm. So in the best of breed pipeline for the training section, we will first construct the feature descriptor, either a shift or hub features for each images, and we're trying to use some keypoint cluster method like k-means, so to cluster its class image to different classes, different cluster, and we'll use some, and we'll try to use the k-means to construct the result best, and we'll construct the result factor for each individual classes. So in detection part, we'll first construct the feature descriptor on the input images, and then we'll try to use the least label methods to match the correct feature vector. This means we'll try to match the correct dictionary, say classes, to each input images. So for the related work, we will talk about like YOLO and FATA RCNN, and I'm not going to talk about the SSD here because it was mentioned in my reports, but it is not in this presentation. And for the faster CNN, actually based on two separate legwork training, and then talk about how to unify the two legwork. The two legwork is actually region-based legwork. It's a couple of base that we'll talk about later, and the fast RCNN. For fast RCNN, it actually it's all about the classification and part. It helps to combine the classification and the box regression in one loss function here. And for regression, for the region-based legwork, we'll see the archbots. How they do for the region-based legwork. Actually use the convolution layer to extract the feature map here, and then use the unique region proposal legwork to extract proposals, and then use the proposal to let the legwork to see which feature to look for the faster CNN. In the archbots used here, it's actually like 3 aspect scale and 3 aspect ratio. This means in total like 9 archbots in the faster RCNN used here. So how did it train? Actually, it first initial the CNN and train the region proposal legwork first, and then use the region extracted by the region proposal legwork to train the detector fast CNN, and then it fix the shared CNN trained from detection and find only the unique layer for the region proposal legwork, and then it fix the shared CNN layer again and fine-tune the unique detection layer, and finally it can verify the whole legwork using the same convolution layer and just for the unique region proposal legwork and for the unique classification legwork. The unified legwork is important because it helps to make it ease the GPU computation, and that's it almost have the real-time performance like 5 frames per second. Then someone developed the YOLO, you only look once. It actually implements the archbots from faster CNN, but instead for looking for each feature cell, it actually uses some grip cell strategy. For each grip cell strategy, it only looks for certain number of the archbots instead. So how did it go? Let's talk about how they train for the multi-objective loss function to begin with. So in the loss function here, it actually consists three components elements like the bounding box requesters, something like to predicted coordinates and width and the height of the bounding box, and the ground truth of the real coordinates and width height of the bounding box for the ground truth one. The second one is the object presenter classifier for the Ichabod base. So and the final one is the object class classifier. Actually, is to classify the object in the Ichabod, which is present object. Then it actually released a version 2 of the Nolo. It actually implements the network in level algorithm for large open layer to replace fully corrected layer by one conversion layer. And then it at the same time it insert one by one conversion layer between consecutive 3x3 conversion layers to increase the non-linearity. At the same time, it reduces the parameter at the same time. So it's really important and concept here. In the paper, it mentions actually reference to Google Ads Inception module. It's amazing because actually it's fast enough and beyond the real-time performance, it actually have like 40 something frames per second. So in this project, I actually is trying to implement tiny-YOLO into real-time onward object detection and use NVIDIA Jetson board TX1 platform instead of the the one you use in general training is like Titan 10. It's not going to happen to in-car situation because NVIDIA Jetson board is really small and portable. And the target object classes I use for this project is pedestrian, cars, stop sign, traffic lights, and trucks. In training session, let's talk about the tiny-YOLO architecture. It actually, to compare with the VGG16, is some similarity like he doubled the fielded number after mass pooling and use mass pooling like 2 by 2, but it's just like less layer. You can see it just have a half raised layer in the tiny-YOLO and use leak reuse activation function instead of a reuse. In training datasets, I use Microsoft Cocoa. And basically, it contains like 80 categories of images or classes and total 300,000 images in the dataset. For my project, it's trying to extract to 5 classes and total 80,000 images for 5 classes. During training, I use stochastic gradient descent with mini package learning, and initial learning weight is set to 0.001 and totally one further 30,000 iteration with the Jetta ratio 0.2. See how it's going. The system I use here, like hardware, is the Jetson Port TX1 and SSD disk to increase my disk space of the TX1 because originally the TX1 you just have 16 gigabytes disk space and I use USB camera instead of the original one and somewhere in here for more angle and for position that I can use, and I use USB to Ethernet converter to connect to my personal laptop, and because I'm doing the in-car real-time real-time detection, so I use 12-volt DC to AC power converter to have my power supply to my TX1. For software part, I use operation system like Ubuntu 16.04, and the core software library installed is OpenCV 3.2 and the Dalal implement with C language and the CUDA 8. Let's talk about the result and demonstration. The video I captured real-time is in-car, in vehicle, in University of the Michigan Dearborn campus. Here are 2 examples of images from the video. Let's take a look at the As we see in the video, it actually has some lots of missing and false detection. So is it the capability of tiny-YOLO? It cannot do any better? We don't know because tiny-YOLO is originally trained for VOC dataset target for 20 cases. So there should be lots of redundancy parameter in the library because we're just looking for 5 cases, but we don't know how to find it and where to look into. Refer to recent published paper. We may try to optimize and test the legwork using the following methods, like using VU aggregation function and shrink the legwork of the YOLO version 2 by fixed fraction in each convolution layer instead of use the whole architecture of tiny-YOLO, and replace the mass pooling layer with dry convolution layer and implement legwork in level after convolution layers in the tiny-YOLO and add average pooling in after final convolution layer, and alter high parameter in loss function during training. But the whole testing and the optimization progress is very time consuming and beyond this project or objective. Here is the reference. That's all for my project. Thank you.